Welcome back to the Art of Math. Like I said, the Art of Math. So I've managed to get away from my precious art career to draw this fantastic drawing for you guys. All right. So today we're going to go over a second application, which is physics, specifically projectile motion. Projectile just means anything that you throw. In this case, this is a human. I don't know if you can tell. Those are supposed to be fingers, and he's throwing a ball up in the air. So the arrow just means it's going up. Now, instead of a ball, you can have it be an arrow, it could be a rocket, it could be a water fountain, it could be whatever you want. Now, in general, this angle doesn't have to be straight up in the air. It could be at a tilt. And to do that, we're going to need some more math called trigonometry, which we haven't studied yet, but just know that you could do that. So if it were thrown at an angle like this, then using trigonometry, we would basically just redo the same problem, but we would split this into two components, which is an upward component and a horizontal component. That's just to give you guys a preview. Don't worry about that too much, but just know we can easily extend this to other angles and not just purely vertical. All right, so here's the question. He's throwing a ball up in the air. We know the speed, it's 5 meters per second. Some of you wondering why I'm using meters instead of feet. Doesn't matter, except later on one of these will be in meters, so it's just gonna make it a little bit easier. Okay, so he's throwing the ball up at a known speed, and let's say this guy is really tall, so as he throws his ball up 2 meters, which is about 6 feet, it's gonna be a little over his head, and he's gonna let go of it at that distance. And we wanna know two questions. This is not timpact, but T of impact. So that's a subscript, which is like an index. So the question is, at what time will this ball hit the ground? That's what this question is asking in really obscure terms. Okay, when will this ball hit the ground? And you might be wondering, how high will this ball reach if he throws it at 5 meters per second? Okay, so to answer that question, let's think how we would do that. So he's launching it at a speed. So clearly, if you've ever lived a day on Earth, you know that this ball won't go into outer space because this guy is probably not Thor or some superhero. So at some point it's going to start to come down. Why is it going to come down? That's right, you guessed it, gravity. So we're going to use this formula over here. So there's going to be some initial height, which is going to be that 2 meters, but then it's going to keep increasing with some velocity. So our velocity is 5 meters per second. Now if you wait 10 seconds, then it's going to go 5 times 10, 50 meters. So the more you wait, the more it's going to keep traveling. However, it's not going to keep traveling forever, as you guys know, and it's going to start going down. So there's a force that's going to start working against it. So although this is going to keep increasing, we're going to have to start subtracting, because this is the acceleration term, and that's going to affect the velocity. So acceleration has to do with gravity, so the A is just a general letter for acceleration, but we're going to use, our A will be G, but remember, it's not just any G, it's a G pointing downward, and that's why this sign is not a plus, but a minus. I mean, theoretically, the acceleration could have been upwards as well, but that just means he throws it and he keeps speeding away faster and faster. Anyway, okay, so it's 1/2 of GT squared. So a lot of you are like, where's this stuff coming from? Stay patient, we'll get to that. So if you plug in G, which is, we know from, how do we get this number of 9.81? People have dropped stuff, they've ran a lot of experiments, and through experiment, empirically, they found that this is approximately the value. So that's your acceleration, meters per second squared. Now we're gonna try to make the numbers a little nicer, so we'll just round it to 10. That's a big no-no if you're trying to have accuracy, but we're just trying to get the concept across. All right, so, or rather precision. Okay, if you plug this 10 in, it'll be 1/2 of 10, and that's where that 5 came from. So for now, let's just buy that this is the formula. So he started at 2, it's moving at 5t, that's gonna be upward, this is gonna go downward. And if we look at this and think of this as a letter y, and these are t's as x's, this is just a parabola. This is the quadratic equation we've been dealing with. So if you rearrange this leading term, this is actually the x squared or the t squared term. The negative means it's downward, so it's going to look like this. So if you think about it in terms of time, the guy's over here. With time, the ball's not traveling to the right. We're just plotting what happens at the first moment in time, second moment in time. This is the height versus the time. So this is time, and that's the height. So we want to know how high is that going to be, and when is it going to hit the ground. So you could, I'm not going to solve this for you guys, but if you go back, plug this into your quadratic formula, and you should find what the solutions are. And by the way, you're going to find two solutions, this one and this one. That will answer the question of when it will impact the ground. My challenge to you guys is, so let's say, these are not the numbers you'll get, but let's just say this is 7 and that's -2. You might get a negative number, so clearly it seems the answer should be 7 seconds. I mean, you'll get some other number. But what's the interpretation of this -2? How can you go back in time 2 seconds? So, I don't know, just think about this, see if this makes any sense to you. Don't just, say -2 is my answer. What does that -2 mean? Do we pick the -2? Do we pick the 7? Think about that. That's question number 1. Question number 2 is this maximum height. If you look at it, well, that's nothing more than finding the vertex of this parabola. So again, you could use your -b/2a for the axis of symmetry. Your b in this case would be, this is your a, that's your b, and that's your c. You would have to rewrite it to be your normal form. Again, go back to the videos on finding the axis of symmetry and vertex, and you should be able to find the maximum height by treating this as the vertex and finding the vertex. All right, so for some of you still wondering, where in the world did this 1/2 come from? Where's this? Maybe a lot of you understood this part, but then that part's a little sketchy. So for the superheroes amongst you, let's go into that. This will be, the whole point of this is just to derive this very formula that we used over here. Okay, so we're going to start with some basic ideas. If we want to calculate, by the way, all these letters I's and F's, those aren't variables, those are just ways to notate which height are we referring to. So this is not an H times an F, this is an index, this is a subscript saying this is the final height and that's the initial height. So if we want to find the final height, and basically like the highest point, we would take the initial height and then add the velocity times the time. So velocity times time is going to give you distance traveled. Now we don't want any velocity, we want the average velocity, because keep in mind, whatever your velocity is, gravity is working against it, so your velocity number is changing over time. So if we take the average velocity, then that's going to tell us where we actually are. So what's the average velocity? Well, since it's not changing randomly for the velocity, it's changing smoothly because there's a gradual acceleration on it, we just average the initial speed, the initial velocity. By the way, a lot of you might be wondering, what's the difference between speed and velocity? Speed is just a number, velocity includes the direction. So to get the average velocity, we average the initial velocity and the final velocity and divide by 2. That's just what, this is just means, this is an average of these two. All right, so for this, we're going to eventually plug that in. Now, how do you find the final velocity? Well, you take your initial velocity and account for how much time has gravity been, or your acceleration, been acting on it. So it's the initial, so let's say this is 5 meters per second squared, and it's been 3 seconds, then this would be 5 times 3. Okay, so that's your final velocity, and this will plug into there. All right, so now we'll plug this into here, and this whole formula will plug into here. And when you do that, when you plug both of these into here, this is what you're going to get. So you're going to get that same initial height. There's 2 of these, so that's 2 VIs, 2 initial velocities over 2, which is just one of them, times that t. That t is multiplying this whole thing. And then you have the 1/2 from here. So that's where this weird term shows up. There's a much faster way to get this, but that involves calculus. It's not hard, but we haven't learned it yet, so I won't use that explanation. All right, so for those of you that were curious, that's how we got this formula. All right, I'll see you guys in the next video. And just know, next time you're throwing a ball in the air, you could pretty much predict how high it's going to go using math.